Good morning, folks. I understand that lab checkouts went pretty well last night. Most people finished, I think, which is good. Any questions on lab 2? Seen lots of obscure behavior. Let me remind you again that there are some examples that are worked out so that all of the libraries are self-consistent for the development boards. They are on the development board page. I'm saying this for the third lecture in a row because some people are still using examples from someplace else, and there's various versions of PT threads floating around, and some of the pins have changed between the big board and the other, and using the raw microstick. So all of these examples, DAC, DDS, animation example for lab 3, keypad example for lab 2, ADC example for lab 3, framed serial peripheral interface example, and the keypad using the port expander have all been validated against the big board. Use these. Again, any questions on lab 2 at this point? It's a good idea to separate out the high-speed synthesis from the low-speed synthesis. High-speed synthesis is production of the samples of the sine wave at around 100 kilohertz probably, and the modulation which has to occur at that rate. It has to occur at the synthesis rate. The low-speed part of the synthesis is when do you turn on and off a syllable. That's on a millisecond time scale rather than 1/100th of a millisecond. And so it is accessible by the thread timer PT get time, which will give you millisecond resolution over a period of 2.5 months or so. Should be long enough. Again, any questions on lab 2 timing or anything else? Well, let's talk about the next topic for lab 3 homework, which is due Sunday midnight, right? The 24th, Sunday midnight. And we have not yet talked about, well, let's see, we talked about the dynamics, and we haven't yet talked about the analog digital converter, which is actually fairly easy to set up and has a new improved example on the dev board page. Nor have we talked about audio synthesis by direct memory access. The first thing we need to do is talk more about what direct memory access is, and then start talking about, well, maybe I'll talk a little bit about the effect of DMA in this lab. The effect of direct memory access, what a DMA controller is a device which is a bus master. So the PIC32 is over here. There's the PIC CPU is over here. There's an instruction master and a data master. So the CPU can issue a memory request against data and a memory request against flash, program memory at the same time. But in addition, there's 4 other bus master channels on this chip, DMA channels 0 through 4, each of which can request data motion on the bus independent of the CPUs. What I'm going to ask you to do in this lab is I'm going to ask you to make sound effects, let's say a barring, something like that, like a damp sine wave at 1 kilohertz. which makes kind of a twangy sound, or like a glass, like tapping a glass with a knife. Bing! And you need to make two different sound effects. What I'm going to ask you to do is to put the whole waveform into a table, a RAM table. So the whole waveform is going to be in the RAM table, let's say 0.2 seconds worth. You may have to slow down the synthesis rate in order to fit this waveform into memory. I doubt if you can put 20,000 samples in memory. I know you can't. So you're going to have to slow down the sample rate, maybe 8 kilohertz, maybe 10 kilohertz, but that's a detail. And the RAM table is going to have the entire waveform, and it's going to have embedded in the waveform the control bits for the DAC. Remember, the SPI DAC has 4 control bits at the top. At the high 4 bits are control bits. There's a 12-bit DAC, requires a 16-bit word, and the top 4 bits are control bits. So this is going to have to be the waveform plus the DAC bits. So you're going to preform the SPI words that you're going to send to the DAC so that they're completely formatted and ready to send. Then what you're going to do when your code requires a sound effect, let's say when a ball collision occurs or the person loses or whatever the effect is, what you're going to do excuse me, is you're going to turn on a DMA channel which is going to copy this table into an SPI channel that's associated with the DAC. By the way, 4 different groups have done this, so it's a problem with my documentation. The SPI to DAC connection is SDO2, and people have been reading that as if it's the output from the DAC. It is the input to the DAC. The output from the DAC is referred to as DACA on the board. You can look at the data sheet, you can look at the schematic for the board and figure out how that's wired, but you need to be looking at the DACA output for the waveform for Lab 2. In this case, the DMA channel is going to copy this table into the SPI transmit buffer. Every time you copy to the transmit buffer, the SPI auto-transmits. That means that this whole copy will occur, the whole waveform generation will occur with no interaction from the CPU. The CPU can go off and do whatever it wants to do, like calculate the positions of balls for the next frame. And the DMA channel, separately and without interaction, will send the sound to the SPI channel, which will copy it through the DAC to the output port. There's just one little twist you have to do to make this all work. And that is SPI to DAC requires a chip select line which is not part of the transmit register. So DMA will not work if you have to use the chip select line separately, because there's no way to send that data to the buffer, to the SPI data buffer. There is, however, an SPI mode which is specifically meant to work with DMA called framed mode, in which the SPI auto-generates the chip select. So in framed mode, the chip select line will be auto-selected, which will have a small wiring consequence on the board, which we need to talk about. So the whole point here is to copy a big waveform to an SPI channel with no CPU, so you can use the CPU in parallel to do something else. So this is hardware parallelism. You can use this DMA for capability for all kinds of things. Whenever you have a mem copy, you can replace it with a copy that does not use the CPU. In fact, you could do any reasonable memory-to-memory copy. But before we do that, we need a little bit of terminology because there's lots of it with DMA. So an event is any system that can initiate or abort a DMA transfer. In this context, an event is equivalent to an interrupt flag. So an event is any interrupt flag can start or stop a DMA transfer without calling an interrupt service routine. So there's no software need be touched. The flag gets set, the DMA transfer starts with no software running, with no interrupt service routine. The DMA controller can detect the interrupt flag. So in particular, for lab 3, the DMA trigger event, or the DMA trigger, what do we call it? The event control will be timer 2, timeout. So every so many cycles of timer 2 will set its interrupt flag. There'll be no interrupt service routine. But instead, the DMA channel will notice the event and start to transfer. A transaction is a single word transfer up to 4 bytes. A cell transfer, every time an event occurs, you get one cell transferred to the destination. A cell can be a word, but it can also be a bigger burst. It can be multiple words. In this case, we're going to send 2 bytes for a 16-bit transfer to the SPI. And a block transfer represents a sequence of cell transfers all happening as one event, as one triggered block within the DMA. So what you would do, what your thread would do, would be to enable a block transfer. Your thread would enable a block transfer. The timer is going tick, 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 ticking away at that synthesis rate. Once you start the block transfer, you'll get multiple cell transfers until you reach the end of the table. If you put the DMA channel in auto repeat mode, oh no, another mode, then you will get cell transfers forever until you disable the channel in a thread. So the total load on the thread is going to be enable the channel, disable the channel. All of the transmit dynamics are going to be in the DMA controller. Block transfer is, yeah, I already said that channel is enabled until DMA channel is transferred the larger of the source or destination sizes. Unless it's and then it's disabled unless you put it in auto repeat mode. But wait, there's more. In basic transfer mode, you're doing a mem copy, and that can include, since the special function registers are all memory mapped, you can do things like read the ADC and copy it to RAM at a data rate determined by a timer, but with no ISR running at all. In fact, that is the only way that you can read the ADC at 1 megahertz, because you cannot do interrupts at 1 megahertz. So you have to use DMA mode to read the ADC at a megahertz. Furthermore, timer 3 can trigger ADC directly with no ISR. So you have a whole hardware chain where timer 3 is ticking, running the ADC is triggering the DMA is copying to memory. There's a pattern match mode. A DMA channel, separate hardware, separate from the CPU, can do a compare between the current byte being transferred and a template byte, and if it matches, stop the transfer. So let's say that you're sending you turn on a DMA channel to send a byte stream out of a serial port. The terminator for a C string is always hexadecimal 0. So you do a match on hex 0, you start the transfer, you go off and do something else with the CPU. The transfer then stops when the string reaches a 0 byte, which is end of string. You can chain channels. So DMA channel 0 finishing can trigger DMA 1, which can trigger DMA 2, which can trigger DMA 3, which can trigger DMA 0 again. What in the world would you do with that? I don't know. I have a hallucination, though, that I could store a list of control blocks for the DMA registers in memory, use DMA 0 to copy the control blocks into the DMA 1 channel, and then chain to the DMA 1 channel. And then use DMA 1 to channel back to DMA 0 to copy in another block. That sounds like a fetch and execute CPU. That's an hallucination. I don't. Channel auto enable mode, I mentioned. It's hardware auto looping. Once you start the channel, it goes forever. Let's say you wanted to make a signal generator. You can run the SPI channel you can run this much faster than you can run main memory. So you can output through a parallel port, you can output up to about 3.2 megasamples a second to a DAC. So you can do quite high bandwidth synthesis by using auto enable. There's also a special function module. On our CPU, there is a hardware linear feedback shift register CRC generator that will operate on a DMA channel and do the CRC extraction on the fly for doing cyclic redundancy checks. We're not going to use that. So you can initiate a cell transfer in a couple of different ways. Remember, a cell transfer is what happens when one event occurs. You could, of course, use software to initiate a cell transfer, but you don't want to do this because that completely negates the advantage of a DMA channel. Now you're having the CPU go off and do something every time you want to send a byte. Why don't you just send the byte from the DMA channel or from the CPU? So you're never, ever going to use software to initiate a cell transfer. However, you can use software to initiate a block transfer. So software is going to enable the block or set up a block and then go do something else, and for the next 0.1 seconds, 10 seconds, however long the transfer lasts, the DMA channel will run by itself with no software interaction. Interrupt details, I'm not going to bother with. DMA transfer can be stopped by manually writing a channel abort command, which is probably what you're going to do in a thread. But you can also, it can interrupt on errors. You can have a DMA channel stop on a divide by 0 event. You could do anything you want. Anything that generates an interrupt, an exception, will allow you to either start or stop a DMA channel. There's a lovely control channel event chart here, which I'm not going to talk about. But The important point is this is a separate piece of hardware that can do memory-to-memory moves for you at high rate in parallel with the CPU. Whenever you are starting to move stuff around from any peripheral to memory or memory to memory for M-copy, let's say you're doing a bitmap for a display screen. If you're going to do an M-copy of a bitmap, a sprite into a display memory, sounds like an obvious use for DMA. So keep this in mind as a coprocessor, but for Lab 3, it is required that you produce sound this way, using direct memory access. So any questions at this point? I'm talking fast. There's a lot to say, but any questions about this? It's hardware, folks. It's separate from the CPU. And it's pretty fast. So, one of the very first things I did with this chip was to use a 7-bit parallel DAC. And it was easy to set up, so that's why I did this. And so the code is fairly primitive. There's no threads here or anything like that. And plus there's a whole bunch of extremely cryptic stuff. Sys keys, setting sys keys. Oh man, this is how you blow your big toe off. Because with changing sys keys, you can unlock the oscillator and change the frequency of execution on the fly. Don't do this. I was doing this because I wanted to calibrate the specific CPU I was using to a different value. You do not need to do this. You do not want to do this. And I was synthesizing sine waves without using direct digital synthesis, so I had to bend over backwards to get the scaling correct. But the critical part here is setting up the DMA transfer. Set up DMA channel 0 and put it in auto mode. Auto mode then, so this is going to, once you start a sine wave, it's going to run forever until you manually disable the channel. We're going to do a DMA set transfer. We're going to give it a source, a sine table. That's a memory pointer. Remember that the name of an array is a pointer. So this is the pointer to the array sine table. Then we're going to give it the pointer of a target. In this case, lat B. Lat B stands for the B port latches, which you just have to know from the data sheet. And I learned from TA last year, Tahmid, who had long since memorized the data sheet when he was like 9. And so this is a pointer to the port B output latch. It's a void pointer in this case. We then say, how many bytes do we want to transfer? Sine table size. What is the width of the target? In this case, 1 byte. And we want to do 1 byte per cell transfer. So every time there's an event that starts the channel, transmit 1 byte. So we're going to take 256 bytes, jam them into the output, into the port B output port, 1 byte at a time. Then we're going to do a set event control to the channel, and we're going to set it to DMA EV start IRQ timer to IRQ. What that says is every time that the timer 2 interrupt flag is set, do 1 cell transfer, transmit 1 byte. No interrupt. Just reading the flag, folks. Read the flag. Start the transfer of 1 byte from the next position of the table to the target byte. And now that we've configured it, we enable it. As soon as we enable it, boom, it starts to make the sine wave. No code in main, no code in the thread, no code at all. And this is what hurts the head, because you just have to remember that this thing is making a sine wave. There is no indication. Oh, you can read the channel descriptor and find out that it's actually sending bytes. You don't have to completely memorize it. But as soon as you start it, no more software. It just runs. You can spend days reading the hardware description of the DMA channel. I have. I think I understand what it's doing. And more days reading the plib description of how to set up the channel. But basically what you're doing is you're configuring a coprocessor by writing registers instead of instructions. And once the coprocessor is programmed by writing registers, it's going to sit there and execute. How many of you have fiddled around with direct memory access control ever? Any? Yeah. On what system? ARM? ARM uses a different kind of control block, arguably more general. Probably not easier to set up. So this is going to be worth a fair number of points because I want you to use it. Therefore, you're going to need to spend some time figuring out how to use it. It's not trivial. That's why it's a 3-week lab. Do not wait to week 2. So once you turn this thing on, it just goes. Now, in the case of your code, oh, let's see. I think that the target you're going to use, so you're going to use framed SPI to SPI2, so the destination is the SPI2 transmit buffer, which is called SPI2 buff, because it's actually a stack, buffer stack, so that the DMA set transfer command that you're going to use is some channel number 0 through 3, almost doesn't matter. It's going to be the name of the source table, which is going to be the waveform ORed with, what are the top 4 bits? The DAC-A top 4 bits, 1011? Or is it 0011? I think it's...
Depends on which channel you're using.
Exactly. I can't remember which one's which right now. I think it's 1011. So we're going to OR this with 0, X B000. Store that in the table so that when we barf this out to the ampersand SPI 2 buff, we have the full formatted version, and the size is going to be table size times 2 because you're going to send, because the counts here are always in bytes and you're sending 2 bytes at a time. And we're going to send let's see. We need the sign table size, the destination size, which is 2, and the number of bytes per cell transfer, which is 2. So the DMA set transfer command that you're going to set up is going to look something like this. How big a short int table can you build on this processor? How many bytes of RAM do you have? You better find out. How many bytes of RAM do you have on the CPU? This should be burned into your brain by now. It's 32K bytes. You might be able to use half of that for tables. There's got to be room for a stack and a heap and other stuff. So you might be able to build a table that has as many as, say, 16 kilobytes. So that would be 8 kilo shorts. So you're not going to build a table which is bigger than about 8,000 samples or so. You need 2 different sounds, so 4,000 per sound. How fast are you going to sample? Well, that depends on how good you want the sound effects to be. The timer 2 setup, assuming you use timer 2 as the control timer, there would be virtually no change for this statement. You may or may not want to open it in auto mode, however. If you want to do one pass through the table, don't put it in auto mode. Just start the transfer and walk away. It'll stop after it gets to the end of the table. On the other hand, if you want to make the table small and make the table be some repetitive function, like a sine wave. I mean, right now you have one cycle of a sine wave that you're sending. But maybe you could do something like this. Some nasty looking thing, sawtooth, store one cycle of that, send it out multiple times until you turn off the channel with an abort channel command. So you may or may not want to put the system in auto mode depending on whether you want to do multiple passes through the table or one pass through the table. And that is going to depend on what you want to synthesize, what your sound effect is going to be. So pretty much the code you're going to need to do to turn on the channel is in the first example on the DMA page. You are going to have to build this table with the DAC control bits. And what we haven't talked about yet is that you have to put the SPI in framed mode. by way of trying to figure out frame mode, I wrote a frame mode version, but I used an interrupt service routine to run the frame mode. Because I don't want to give everything away. You cannot use an interrupt service routine. This is for the framed example. You have to convert the framed example to DMA. If you look at the interrupt service routine, we're doing a DAC config channel A, DAC channel, waiting for SPI to be done, writing the other channel, waiting for SPI to be done. What's missing compared to the interrupt service routine you have just been writing? What's different about that? It has two channels rather than one channel because I was doing both channels. I heard the magic word.
Chip select.
There is no chip select because it's framed. So the chip select is auto magic. It just happens. And the reason it just happens is when you do the SPI setup down here in main, when you do the SPI channel opening channel 2, mode 16 bits, blah, 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 master mode, clock enable, reversed, whatever it is, SPCon, framed, F-R-M-E-N, Fremen, and Frempol. That's frame polarity. I don't even remember what the other one is. So this turns on the auto frame mode, which pulls a pin up and down for you to do the chip select. However, you don't get to choose the pin. Oh. You don't get to choose the pin. And in fact, the pin that's required is not the one that's wired on the board. Oh. So what you have to do, you want to flip the lights off over there so you can admire the artwork here. Ah, better. Thank you. What you're going to need to do is you're going to have to pull a jumper off of here, off the chip select, and you're going to have to jump that over to RB10 using a jumper wire, because RB10 is the hardware chip select line for channel 2. So RB10 is going to be hardwired to here for the purposes of the DMA driven framed mode SPI. Is that clear what's going on there? Any questions about that? Add one wire, jump from RB10 up to the top head of the pin of the header. You run it to the bottom pin of the header, you blow up a pin on the pick. Put it on the top pin, not the bottom pin. So what you're going to have to do is merge code from two examples. There's the DMA setup code on the DMA page, and there's the framed SPI on the SPI page. When you're using the framed SPI, what's going to be in the interrupt service routine to run the SPI channel? Nothing! There's no interrupt service routine. Merely, you are going to enable the DMA channel, which is going to traverse the object, traverse the table, spit data out to SPI2 buff because that's how the transfer is set up. There will be no code anywhere that does a write SPI because the DMA channel is going to do it for you. Since you don't need a write SPI, and that's the only thing in here, there's no interrupt service routine.
So part of what this code is doing is it's waiting for the SPI transaction to be done before it starts writing again. How do we get?
No, it's not.
It looks like it is. It's while SPI2 stop bits.
Oh, yes, yeah, you're right. You're right. You just better make sure you don't write too fast.
Okay, so you just need to set the rate on the DMA channel such that it won't start overwriting itself before the SPI is done transferring.
You have to make sure that the timer is set up. The timer event is set up to a low enough speed that you don't overwrite the SPI channel. Yes, that's correct. So how low a speed is that? Well, if the SPI is running at 20 megahertz, that corresponds to a 16-bit transfer in 3/4 of a microsecond. So if you're running at 44 kilohertz, that's 21 microseconds, right? So that's plenty of time for audio synthesis. It's plenty. The SPI channel is plenty fast enough. You can't get a megahertz out of this, but you can get a bandwidth up. I think Tom had managed to push this up to 500,000 updates a second, doing every optimization he could think of. But you're going to probably be running it at more like 10,000 samples a second. Yes?
Is there any incentive to split up your data tables for the sound bites and the sprites across data RAM and flash storage?
Oh, interesting. So, because flash is a different target, is a different RAM target than RAM, where should you put these arrays? If you put them in flash, then the data transfer is going to compete with the instruction master of the PIC32 because you can't hit flash twice in one cycle. Do you need to hit flash twice in one cycle? I don't know. I haven't run that experiment yet, but that's an interesting experiment, is compare the speed of transfer out of flash to the SPI versus out of RAM. Now, I suspect that since you're only doing 2 bytes every 50 microseconds, that you're going to get negligible effect on the execution of the CPU. So you could probably put it in flash and put really big tables in flash. Because how much flash memory is there? That's why it's called a 128. It's 128K of flash. So you have 4 times as much flash as you have RAM, so you can put bigger arrays in flash. And you remember how to do that? I mentioned it just once in lecture. If you use the keyword constant short, C-O-N-S-T short, then the compiler recognizes that the program will never change it, cannot change it, and puts it in flash. The dog's walking back and forth in front of the motion detectors. So, this should be enough info to do the last problem of the homework, which is a DMA question. However, prudence suggests that by Friday you read the question so that you can ask questions about the question, sort of meta questions. Okay. Also think about, what do you want to see clarified here? There's several moving parts. There's a whole new piece of hardware which only two of you have ever seen before, which is DMA. Then there's modification of the SPI channel to framed mode and modification of the table to include the control bits for the DAC. And it all has to be in the same place at the same time, or of course it doesn't work. Oh, I'm wrong. It's channel B is B. Channel A is just 3. Of course, you could use channel B. Let's say you wanted to play stereo out of DAC A, channel B, and channel A and channel B. You wanted to play stereo. How would you set up the table? Or is it possible?
So I would interleave the words for channel A with the words for channel B so that you'd send one right after the other. But the problem with that is that now you're sampling it, and every other sample is. So I don't know a good way to send them both at the same time.
So you're quite right. That would exactly work. And then the question is, if there was a one sample offset between the two channels, would you know? And if it's at 10 kilohertz, you wouldn't, because your time resolution, your acoustic time resolution is probably, if you're very good, is probably 5 milliseconds. So you wouldn't notice it, and that would work exactly that way. You'd have interleave the control words for channel A and channel B in the table, and it would play both channels alternate samples. So you'd have to sample twice as fast. It means the table would be twice as big, but you put it in flash.
Also, you need a separate low-pass filter on both channels.
Yes, you probably would do that, although for a game like this, you might say that harsh sound is actually, harsh, nasty 8-bit sound is actually a positive thing. It's not a bug, it's a feature. Depending on the aesthetic you're going for, if that's even the right word in this case. What else? Any other questions? Let's see. So there's a lot to keep in mind. There's lots of pieces that are all moving and whole new hardware to learn. But not too much different setup, because a lot of the work is done for you by PLab. Okay, I'm going to be in lab in a few minutes and be there all afternoon till 4:30.